So my topic today will be on the use of the libraries and how they lead to the faster development and commissioning across platforms and industries. So brief little intro about Maskine. We're a small systems integrator focusing on the software development side of the PLCs. We don't sell any hardware or build panels, but we happily program them. Because of this and because of our diverse spread of industries, we've used CODESYS in automotive, brain controllers, food and beverage, valve exercisers, blowers, refrigerants, and a few other items. Because of all of these things and all of the different platforms that CODESYS is on, whether that be IFM, ABB, Cybergus, or even like a Raspberry Pi, we decided to develop an internal library that is hardware agnostic, can handle any CODESYS platform that we work with, and requires as minimal adaptation for whatever system that we're in. So the topics today that we'll be covering are going to be the fundamentals of the library, kind of what it is, the library, the benefits and the usability of it, some of the challenges that the library has faced, the improvements that we have made, how the exploitation of OOP and how we've used it in the libraries, some of the more advanced uses of our internal library, the code in action uses, and then best practices. So first off, what is a library? Simply put, it's just a collection of POUs, DUTs, function blocks, and programs, or any other component that is used within the PLC project. They'll provide tested code for use in multiple projects, improving scalability, maintainability, and reusability. The version control is utilized to ensure updates can happen to the code base without impacting any existing systems. So any updates you need, you don't need to worry about causing new problems. And finally, they should contain both logic and the documentation. Having it all in one location makes it very simple for both the developer and anybody on site to debug and kind of work with. So in CODESYS, libraries are standard and utilized heavily, whether that be TIONs, RTRIGs, they're all coming from a library. Everything comes from a library, right? But with that, the question is no longer what is the library, it is why do I even need one, right? So the benefits to using the library, right, is going to be the code reusability, the standardization, maintenance, scalability, and collaboration. So for code reusability, why reinvent the wheel? Every project I've ever had has had a digital input, digital output, analog input, and analog output. I'm not going to remake that block. I've made it a dozen times. I don't want to make it anymore. So why would I make a new one when I can reuse tested code? For standardization, by using the library, every project gains access to the same base function blocks and standard naming conventions. So it not only allows for faster development times since you no longer need to reinvent anything, it streamlines project collaboration since your internal library can be picked up and used by any internal team member. This has saved us significant time in the past when reallocating resources from one project to another, whether that's somebody going on vacation and needs a stand-in. It is very easy to pick up an existing project that you don't know anything about because you understand how the code is set up. Maintenance-wise, when developing a project, bugs are inevitable. Countless times have I had to copy code from one project to another, and that code has a bug in it. It happens. So rather than copying the code and resolving the bugs in these kind of lower level function blocks on a per project basis, investing time in creating the library and doing the same tests one time and reusing that library across all of the other projects and platforms saves you significant commissioning time, and you can fully trust the functionality of your internal libraries after that initial testing. Scalability wise, we are able to break down the function blocks and utilize the object-oriented aspect of CODESYS and effectively turn your code into Legos. Makes it very easy to build up your system into using them as building blocks that kind of all slot together. And then collaboration-wise, you can break the library out into chunks with one developer focusing on one set of blocks while the other develops another set. So you could have Steve working on standard I/O while Robert works on motion control, right? Two very different things, but standardized nonetheless. So continuing with the code reusability, the use of the library provides a very easy way to ensure systems are standardized. So whenever I'm starting a new project, the first thing I always ask myself is, have I worked on any projects that have similar functions or devices? What can I reuse? Right? I'm not wanting to remake everything. So once that's determined, I make my projects start pulling in code from all the different systems that I can. And because they all have pretty much the same IO, right? Analog or digital IO, VFDs, I don't want to go into 18 different projects to grab 18 different blocks. Right? It's not time efficient. Um, so, and that's not even to mention if multiple projects have this similar function block across them, now you need to worry which one is going to be the best for your system. It's just a lot of headache for not a lot of reward on that end, right? So by using the library, it acts as a container for all of these common function blocks, and I no longer need to go through all of these different projects to find something. So once the library has been tested and deemed bug-free, then all future projects will not have that, will have bugs, will not have bugs originating from the library. So you'll know that you've built your system on a solid foundation. And then finally, for the new hire onboarding, it sets it up in a way that I can point a new hire to the library and say, here, go build a stoplight intersection using the library. There are examples of each function block in the library. Go wild. It lets them explore, kind of get a feel for how the programming aspect of it all works. Lets me guide them and provide them with examples, gives them experience with code that they'll be using on the live machines, and enforces coding standards all in one go without requiring me to helicopter and kind of parent them during that process. So it lets me be very much still hands-on and still involved in their training, but with adequate resources. So some of the traditional libraries problems that we've faced is there's not really an easy way to port code between platforms. And devices, especially VFDs, have slight variation in control. And then as well as HMIs tend to behave differently. So when developing the library, platform differences, HMI differences, and manufacturing differences do cause those pain points. Some code bases allow linking of like the I stars and the Q star variables in the IO tree, while others require it within some kind of GVL. And then HMI wise, the protocol of being either OPC, Profinet, Ethernet IP, ADS, Modbus, whatever the case is, it can be annoying to deal with and handle appropriately depending on the system. So with those kind of problems that the libraries face, we ended up making these improvements. So PLC wise, of course, using CODESYS, we use exploit and kind of abuse OOP to allow consistent objects in similar devices. And because CODESYS is used in so many different platforms, we implemented it using the lowest level dependencies as possible, and that allows us to create the function blocks to be as hardware agnostic as possible. So now an analog input could be a voltage, it can be a signal over Modbus of 420 milliamp, it could be some resistance, it does not matter. It's still an analog input at the end of the day. The HMI portion, though, was definitely the more difficult part. Because each HMI platform has different requirements, what we ended up implementing was kind of two-tiered approach for it. We have a JSON interface, and we also use a standard HMI structure. So the JSON interface and the JSON strings inside of it allow us to connect to more advanced HMI platforms that can handle that kind of parsing. So some examples that we've used on live equipment would be like TwinCAT HMI or Ignition. And then for like PLC visualization, which doesn't natively support like a JSON parser, nor would it need to, we use that base HMI structure. So inside of that PLC library, what we've done is we say, anytime a command over the JSON is received by the PLC then takes that command and writes to the HMI command structure, and then that goes into the logic. So everything is handled in a very clean way. and allows for a streamlined, consistent, and simple way of handling commands and status and configurations. So the exploitation of OOP. So inheritance, polymorphism, and encapsulation are the fundamentals of OOP. So the library is going to encapsulate the interfaces, function blocks, and methods, enabling this advanced design architecture and utilizing the inheritance, polymorphism, and encapsulation listed here. So inheritance allowing for the simple extension of the function blocks. Best example of this is going to be VFDs, right? For the most part, VFDs behave the same regardless of manufacturer, at least on a kind of base level. They're going to have a command to move forward and backwards. It's going to have a speed set point and a speed feedback. There's probably going to be some error handling for speed timeouts, for a motor stall, maybe some current monitoring. And typically it's going to have a control and a status word. But that control and status word is going to differ from manufacturer to manufacturer. So because of this, what we've done is we kind of create a base VFD block, and then everything extends off of that. So the base VFD block, or VFD interface and block handle the errors, the state machine logic, and the HMI commands. Then once we get to the more hardware specific aspects in that base block, we include some methods for overriding and extending later on. Once that base block is done, we'll extend it to whether maybe a VFD KEB or an ABB or a Scala drive or whatever the case is, override those hardware specific methods to handle the actual device IO control. So that's going to be setting the outputs, controlling the control word and the status word, and mapping those to the common aspects of the VFD block. And then using the extended VFD blocks and the coding style and behavior will be identical. It enables the use of that VFD interface for passing devices around if needed between like equipment modules and sequencers. So this way, you've got a shell and you can fill the shell with whatever you need it to be, but at the end of the day, it's still that shell. It still holds and still has that same structure. It really enables you to make your systems hardware agnostic. So if a customer comes in and changes manufacturers, it's very, very easy to switch it up. So by exploiting the object-oriented programming provided by CODESYS, it makes it really easy to handle faults, errors, and device modes for every device in the system. So I like to imagine it as like a set of lock and keys. By using the interfaces, your lock, a key kind of thing, your equipment module being the lock here can take in any key or child device as long as it has that same base device interface. So this lets me pass errors automatically between any of the child devices to the equipment module. It lets me handle all of the resets and mode controls as well. So any time I need to switch from auto to manual, good to go. I don't even need to worry about it anymore. So a great example here is we have a customer that's using 2 different VFDs on their system, just depending on what is available and the cost of it. So we set it up so that the system utilizes this interface and handles everything using the ITF base device and the ITF VFD that we've defined. And it allows them to easily switch between the VFD options without their sequence being impacted. The code became very clean, very modular, and it's independent of the hardware that's available. So especially if you have a customer who ends up making the same tool but changes up some hardware every once in a while, this makes it very, very easy to streamline and develop. So a little diagram of kind of how some of those commands are handled and works. By utilizing the JSON, your PLC and your HMI communicate with ease. It no longer matters how many OPC tags you have available, how much processing you have. Deployment to the HMI is also a lot simpler since you no longer need to actually deploy anything to the HMI. It all comes from the PLC runtime. And by using those same structured JSON strings across various PLC and HMI platforms, it standardizes our HMI design. It standardizes that design, the development, and the code base, regardless of what our end customer's use case is. Because the JSONs are hosted in the PLC runtime, they can be viewed over OPC, ADS, or whatever other protocol being used. And in order to make it all set up, we've got it so that any of the CODESYS-based PLCs, whether that be IFM, Phoenix Contact, ABB, whatever the case is, they can utilize this library. And many of the HMI platforms can support, or at least be made to support, JSON strings. In order to make the PLC library agnostic of the hardware, we've added those methods and properties to assign raw values and handle all the hardware aspects of it. That way, whether it comes in over Modbus, Ethernet IP, Ethercat, or standard digital I/O, we can handle the I/O without editing the base library. It makes a very, very clean and hardware agnostic system. So here's the code in action. Personally, I think this is the fun stuff. Out of all of your projects, how many of them have had a customer ask for an HMI change, only for another person from the same customer ask for a different change? How many times have they asked for a new status variable in the HMI or a new command that was not initially considered? For me, it is every single project. And don't get me wrong, the customer is always right, and I fully agree. However, I really wish they were right earlier on when I was developing the HMI. So because many customers ask for these HMI changes without really realizing what actually goes into doing that change, and by implementing this library, we kind of simplify that process down to a single change on the PLC side. So in order to add in commands to the HMI, you'd call either a m_add command or add cyclic command. The main difference here is the intent behind it. So a cyclic command is only showing when a condition is true. In the code kind of shown here, this add example commands Boolean allows the HMI commands to be shown or removed. So whenever it's true, it shows up, and it's false, it's hidden. One quality of life benefit of doing these cyclic commands that I don't need to hide buttons or disable buttons from the operator during the runtime. So if I don't want an operator to be able to move forward, I can just get rid of the button. It prevents them from having to set it. It prevents me from even thinking that it's on the HMI and having to worry about handling it. And I don't have to worry about accidentally forgetting some user security level that allows it to go forward, or some condition that disables that button. So by utilizing kind of this JSON handling, we dramatically reduce our HMI development time. And no longer do I need to create a new faceplate or icons on the HMI. The device icon is going to be automatically populated based off of the PLC string and as some text runtime, or text in the runtime, I should say. And the color, the status, everything is just pulled up from the PLC. All the developer needs to do is just drag the device icon onto the HMI and add the JSON path as the parameter, and bam, you've got an entire faceplate done and done. At the end of the day, this resulted on your HMI side, one faceplate and one device icon, and that is it for every single device. They all work off the same thing, way easier to maintain. So for getting things to kind of show up on the HMI status tags, we've added this add status method. So it adds the example, in this case here, this example value tag to HMI, lets you decide what color you want. So if it's an error, very, very easy to do a little select statement and just toggle it between gray and red. Easy. Lets you bring attention to the items onto the HMI and maintain a very consistent color scheme, since your color source is posted from the PLC side. It saves significant amount of time, since you don't need to create new buttons, new tags, new faceplates, none of that. It's just done and done, added in the PLC, good to go. And because we apply this to our library, a VFD is always going to have a speed feedback, or we're always going to want to see that on the HMI as a status. It comes in standard with our library, so we always will have it available. It makes it very, very simple to implement. The other benefit here is that it can avoid PLC downtime. So since these all happen during the runtime, they can be done during an online change. So I've worked on large mixers in the past that when doing a download, brings the entire production line down. So we are unable to do downloads. And if we do, they need to be scheduled out and planned for weeks in advance. And sometimes that's just not really a pleasant option to be in. Bad situation, right? So as soon as we were able to implement this library, anytime they ask for a new status tag on the HMI, we could just do an online change because we would, let's say, already have it in the PLC variables, or it's adding a Boolean tag or something small. Then we can just push that as an online change and add it to the JSON. And since it happens during the runtime, it will not bring the system down. So one use case that we have here is just kind of communications. I've gone into the JSON handling, which incredibly helpful, isn't the only real benefit to using the library. Since we've got customers who use 4 to 20 milliamp or Modbus or whatever random hardware they can possibly find, so they can make their machine as cheaply as possible, they'll use whatever they can get their hand on. So to allow them to kind of mix and match whatever I/O they need, the library box in a simple toggle switch on the HMI that selects between Modbus or 4 to 20 lets the customer decide where the input source is for this system and frees us up from a 2 a.m. phone call because they're on the East Coast or something and need to change over from 4 to 20 to voltage or to Modbus or something, right? Lets them mix and match, saves us a significant headache as they're no longer needed to support for like simple I/O changes, and enables the customer to make their product as cost effectively as possible. Win-win all around, Another classic use of the library would be just kind of bundling of utilities. So bundling up such as PIDs, scales, filters, ramp generations, these things into a single location for easy reuse results in consistent, repeatable signal processing across all of your machines. So prior to making our internal libraries, I'd made the same linear scale function a dozen times. And of that dozen times, I probably messed it up about half of them, since I would always forget to add in that initial minimum value. Now, I don't even need to think about it. It's there. I've already got it available, good to go. Whether it's scaling, PID, signal, or what other common function, having them all in one consistent location simplifies your development and provides consistency across all of your systems. And then finally, we had a project that has, or two separate projects. Project A is a gas detection facility where they had a bunch of sensor inputs, and then based off of those alarm levels, or based off of the sensor inputs, we raise alarms at certain levels, like a low, a high, and a high. And depending on the alarm level, it needed to shut down some refrigerants, or some chillers and testers for refrigerant systems. And then in Project B, it is an engine and vehicle mounted for a snowblower. So this system, both of them, one of them is using a Burgess PLC, the other is using an IFM PLC. Both are running in CODESYS. So we used the same library on both. Now, albeit these systems aren't the largest, there was probably 100 points of I/O across both of them combined. When you start getting into 500 plus I/O devices, it adds up, right? So in both projects, the same library is used. The handling of the logic is consistent and allowed for rapid development due to the code reuse and standardization. Didn't need to copy and paste. It's just good to go. In both projects, the engineer who actually developed the code did not end up commissioning the projects. So because of this, the commissioning engineer was A-okay, had no issue identifying any bugs if there were any in the code, since the logic was standardized and readable. He had trained on that library, knew the library, didn't have any problems. And since the project used the JSON handling, we only needed one HMI device icon and one HMI faceplate. The JSON handles the rest. Automatically handles everything else, good to go. So for a small system, it may be sure it's unnecessary. However, take a system running 500 plus devices, all with the different configurations, scaling, tags, different devices, analog, digital I/O, servos, but also custom stuff like a weather station or like a J1939 engine and other items. It doesn't matter what type of device it is, the library and the JSON can handle it all. So in the library side of things, there's nothing worse than getting a new project and it not really having any proper libraries. Everybody's opened a project, didn't have the right dependency, and you have to either find it online, contact support, or hope you can install it from the project, right? So it can be a struggle to really get the exact correct library versions of the code that you're working on. So to mitigate that, you'll want to implement pretty clear version control. The way that we've just styled it is we utilize, it'll be the build, the patch, the major rev, and the minor rev. So for a project in 3.5 SP20 patch 6, it'd be 20.6, and then we'd say major rev 2, minor rev 5. Pretty simple, makes it very easy for us internally to understand where in the code we're looking, at what version we're at, and what it will be compatible with. Documentation should be, in an example, should be included within the library itself. So many times you're going to be on site that doesn't have internet access, and it's a pain to get access to any kind of documentation. You have to pull it up on your phone or use a hotspot, and that can be problematic. So by including all the library documentation within the library itself, as well as examples, you enable your field engineer to read documentation regardless of the site and its network. So separation of the libraries by domain and creation of this container library kind of go in hand in hand. In order to enable consistency, compatibility, and collaboration, you split up the libraries by domain. Once the libraries for each domain have been made, you can package them all up into the same major revision, group them into that container, and use that whole container in your project. So now your system has access to all compatible libraries in one easy location. You're good to go. Backwards compatibility wise is crucial, especially within the same major revision. If you are working on the library and you upgrade and it no longer is backwards compatible, it can definitely cause problems if somebody needs a fix that was applied in the newer versions, right? So bugs happen, and you don't want to get stuck into the position where you can't upgrade the library because of that, because it's no longer compatible, but need to upgrade it to resolve the issues. So by enforcing the strict rule of compatibility within the same major revision, it becomes a non-issue. I like to use the major revisions to indicate whether it is or is not compatible, because there are some major jumps when you go from major rev 1 to 2. And if I need to add an edit in on an older major revision, I can do so, right? There's nothing stopping me from adding a new minor revision to an older major revision. And finally, there's a reason nearly every Python package is stored on Git. Every software version control is critical. It's why there's a reason why you shouldn't have a million files saying library 1, library 2, library final, and then library final, right? Everybody's got all those files where they just increment the counter, right? So now, since libraries, they can typically be, or they're usually compiled into binary code and become unreadable into Git, you can drop them into Git using like LFS. The only feature you kind of miss out on is that merging the viewing code from source control. But in the library side, it's a lot less critical to do that, since you tend to be working a lot closer on the library, and it's usually one person on that portion of the system. So the key takeaways, it enables the code reusability, object-oriented design, and standardization. Program error reduces the program errors, accelerates your development time, improves onboarding, and supports maintainability and scalability. It reduces that development and commissioning time, improves your code quality, and reduces that new developer startup, makes your documentation easier to handle, your system's consistent, and your code standardized. Overall, it's absolutely worth the time investment and has saved us between 10 to 30% on project development time over the course of maybe 10 projects since we've completed the library. So that adds up very quickly, especially as you get more and more work coming in. The one major key takeaway here then is that it's developed once and you get to reuse it everywhere. So once you've got it, it's yours and you're good to go, and you can kind of use it as much as you need to on any project you possibly need. I appreciate everybody's time, and I look forward to hearing your questions later on.